Hello, AP Physics 1 students. Let's take a look at the example of an object coming down an inclined plane, but not sliding, in this case rolling without slipping. So let's draw our generic inclined plane seen from the side, inclined angle theta away from the horizontal, and here's going to be our object that's going to roll down the inclined plane. Now I need you to draw this object rather large, maybe exaggerate it, draw it larger than you think, because if it's too small, you really won't be able to see what's going on. We're going to set some parameters here. We'll say it starts at a height of h naught, and we'll tell you the shape of it. Specifically, we'll be looking at a disk, although if it's a different shape, a different distribution of mass, we'll get a different answer, but this is specifically going to be a disk. And we'll make it nice and easy. We'll say it starts from rest. Okay, so our first job now is to draw a good free body diagram. Remember, it's not just about drawing where what forces are there, but now we have to be very careful to draw where those forces are coming from, where they're applied. So pause the video, go ahead and draw your free body diagram. Okay, what force do we always start with? Of course, we draw mg first. Which way is the point? Straight down, of course. Where does it come from? It comes from the center, right? The force of gravity acts on the center of mass of the object. We'll assume there's a uniform distribution of mass here, so it's going to point right from the center. So there's the center, which is also going to be our pivot point. We're imagining it rolling around that point, and there it is pointing down from the center. It is traditional to use capital M for a rotating object, so you might want to change yours to that. I will also say it has a dimension capital R for its radius. That's also very traditional. Okay, it's on a surface, so of course it's going to be a normal force pointing which way? Of course, perpendicular to the surface, but now it's really important to show where that normal force is coming from. Did you do that? Yeah, up to this point, it's never really mattered, but this is the first time when it really absolutely matters. So let's think about this. Normal force only appears when there's a surface. Normal force comes from the surface, which means you have to draw the normal force originating from the contact point between the object and the surface. So it's got to actually come from here. So make adjustments as necessary to your free body diagram. And it should then point directly up through that pivot point. So make it look exactly like mine. And the other forces on the free body diagram? Well, of course there are. This object isn't sliding down the inclined plane, it's rolling. And if it's rolling, something has to be catching it, allowing it to roll. That's got to be a friction force. And again, it's super important we draw where that friction force comes from. If the friction comes from the surface, it also originates at the point of contact between the object and the surface, and so it should look like this. Of course, it's going to point up the incline, opposing the motion of the object down the incline. Okay, so there's our entire free body diagram. And now what do we do? Well, of course, we write sigma F equals ma, and we build up our sigma F statement. Now, I have skipped the step of drawing all the stuff I usually draw off to the side, velocity, acceleration, net force. If you did, I'm proud of you. Thank you so much. I appreciate you doing that. I'm going to run out of room on the slide if I do that, though. So we know what's happening, right? The object's clearly coming down the incline. So we're going to call down the incline the positive direction. It's also accelerating in a translational sense, so we know the net force is going to point down the incline. Fantastic. Okay, so pause the video here, write your sigma F statement. Okay, now it is an inclined plane, so yes, what we really do is, of course, we resolve the force of gravity into its component, one component down the incline, one component into the incline, but I'll tell you now, the expectation is that we should be at a point in the year where you don't have to draw that separate step. If you did, it's okay, but I want you to challenge yourself to recognize that you know what component is going to point down the incline and what component points into the incline. Okay, so we know it's going to be mg sine theta down the incline opposed by the force of friction, and so it's mg sine theta minus force of friction equals ma. And here, instead of leaving it as the generic m, I am writing it as a capital M. I'd like you to do the same throughout the rest of the derivation. Okay, nothing more we can do this, but now we see we have to worry about the fact that it's rolling, and it's not just moving, it's going to be accelerating in an angular sense, so we have to do a sigma tau equals I alpha statement. Now for this, we will do a little more detail. We have to know what our positive direction is rotationally. So pause the video here and draw what you think should be a good positive direction for rotation. Okay, so I hope you realize that since coming down the incline and rolling this away, yes, we are going to call clockwise the positive direction, since that's the direction of its angular velocity. Okay, so now we have to, we got to think about what force or forces are contributing to sigma tau. So let's make a list of the forces to see whether or not they produce torques. So here's a listing of the forces, mg, normal force and force of friction. So I'd like you to pause the video and go through this list for yourself and identify which force or forces are producing torques about this pivot point. Okay, let's take them one at a time. Let's take the force of gravity first. Is this producing torque about this pivot point? Hopefully you realize the answer is no. But what's more important is you know why it's no. So we think about the equation for torque, which is RF sine theta, where R is measured from the pivot point to the application of the force, and you should be able to see, well, hey, the force of gravity is acting on the pivot point, so the value of R is literally 0. So no torque there. Okay, how about normal force? Okay, so hopefully you also identify that normal force is not producing torque, and your reasoning might be, oh, well, it's going right through the pivot point. Sure it is, but is it because R equals 0? Let's think about this, right? R is measured from the pivot point, that's here, to the application of the force, that's over there, and so let's draw that on our diagram. There's R. From the pivot point to the application of the force, is that 0? No, absolutely not. So is normal force producing torque? Well, wait a second. Remember, to really show this, we have to align the position vector with the force vector tail to tail. So let's shift it over there. So now they are tail to tail, normal force and position vector. And what angle is there from position vector over to that normal force? Haha, that's 180 degrees. RF sine theta is sine 180 degrees is 0, and so that's the reason the normal force produces no torque, because there's a 180-degree angle between the position vector and the normal force vector. Okay, now let's go on to friction force. Is it producing torque? Well, I hope so. Otherwise, we got a problem here. But yes, of course, it's definitely producing torque because it's certainly off axis and it's not pointing towards the pivot point. It's not pointing away from the pivot point. The angle is not going to be 0 180. And so, yes, friction force produces a torque. Is it producing positive or negative torque? Take a look at the diagram and see if you can figure it out. Okay, I hope you can see that the force of friction is tending to rotate it this away, which is the clockwise direction, which identifies positive. And so, yes, indeed, that there is a positive torque from friction. And this is a tau, right? Make sure that's a tau. Make sure it's a nice curvy tau there for torque. Okay, and so now we can start substituting some equations here. So, of course, the friction force is going to produce a torque here, RF sine theta, where R is just the radius of the disk. I told you it is a disk, and so we'll just use the moment of inertia for a disk, which is 1/2 mr squared, an equation that you do not have to have memorized. You can just be looking at your chart. Okay, and then we start to think about some things here. So what angle theta are we talking about? So I don't have to shift that position vector here again if you don't, we don't really shouldn't have to do that. We should definitely be able to see there's a 90-degree angle between R and F, and so theta there is going to be 90 degrees. And then we could also say, wait a second. Alpha, how does that relate to the acceleration? Well, if it's rolling without slipping, we know the velocity of the center of mass is related to the angular velocity by VCM equals R omega. If we just divide both those sides by time, that would be velocity over time. Really, let's think about it as a delta, right? Delta V over T on the left-hand side. Delta V over T is acceleration. The right-hand side is R times delta omega over T, and delta omega over T is alpha. And so we can say for an object rolling without slipping, we look at the center of mass acceleration is related to the angular acceleration by A equals R alpha, and so we can replace alpha with A over R. So let's do both those things. So sine 90, of course, is 1. That's going to go away. Alpha is replaced by A over R, which now I'm going to write as the capital R as the radius of the disk. What's going to happen here algebraically? Right, all those R's go away. One factor of R cancels here. One factor of R cancels one factor of R on the other side. All the R's go away. And we're left with the force of friction in magnitude is equal to 1/2 ma. What could we do with this? We can substitute this right back into our sigma F equals ma statement. Okay, so the goal here is to develop an equation for its incline. So substitute this in for here and rearrange and solve for the acceleration. Let's see what you get. Pause the video and try it on your own. So here's the force of friction substituted into our sigma F equals ma statement. And then notice, all the masses go away, that's gone. And when we rearrange this and solve, we should be getting 2/3 g sine theta. Yeah? Is that working out? I hope so. Very good. Okay, let's also solve for how fast it's moving at the end of the incline. So I think the best way to do that is using our time-independent kinematics equation, where the acceleration is going to be 2/3 g sine theta. Let's be very careful. I gave you the starting height of the incline. Is that delta x? Oh, of course not. Delta x is going to be the length of the incline, so we're going to have to worry about that as well. How can we relate those? Well, we can just use trig. We can say sine of theta is opposite over hypotenuse. That's going to be h naught over delta x. So we can solve that for delta x and substitute it in here. V naught is going to be 0, and acceleration is 2/3 g sine theta. Okay, so put that all together on your own and see if you can develop an equation for its final translational speed at the end of the incline. So here, just rearrange for delta x by swapping sine theta and delta x. So delta x equals h naught over sine theta. So v naught is 0, that goes away. So 2 times the acceleration, which we found is 2/3 g sine theta. And delta x is h naught over sine theta. What happens here? Yep, sine theta is going to go away. Don't forget, of course, to take the square root. And we should end up with this, yes? Square root of 4/3 gh naught. Okay, this all looks really nice, but does it make sense? Well, why don't we compare it to something that we're more used to, an object coming down an inclined plane, maybe if it were sliding down an inclined plane without friction. We've looked at that example many times, both from a kinematics perspective with forces and also an energy perspective. And you might remember that if it goes through a height change of h naught, and if it has no friction on the incline, then it would end up with a speed of square root of 2gh naught, and it would have an acceleration of g sine theta. These are very sort of standard solutions, and if you really want to, you can try it on your own, maybe somewhere else. But now we can compare. Well, look at this. So we're sliding down a smooth incline, we get square root of 2gh naught. Now that it's rolling without slipping down an inclined plane, we get something that looks kind of similar. It's got a square root of something gh naught, just got a factor of 4/3 instead of a factor of 2. In terms of the acceleration, it would just be the force of gravity component mg sine theta making it happen, so just a equals g sine theta, and here we get a equals 2/3 g sine theta. So again, we can take heart in the fact that it looks like our old results, just with some extra factors or some different factors in front.